Hello and welcome to the course Design Board Fields with Confidence. In this video, we will go over the answers we came up with to the questions of part 2 of this course. Now, if you have not read the questions throughout the different chapters, please do so first and try to answer them yourself in order to get most insight out of it. So, question 1.1 was about how a temperature profile would look like when we say, well, let's assume we don't have any peak powers for cooling, we just have a baseload power. So how would that profile look like? Now, of course, it's really easy to just put it into GHE tool and see what it would look like. But if you don't have any peak powers on a monthly profile, what basically happens is you just have your monthly energy load, because your yearly energy load gets converted to a monthly profile. And the temperatures during cooling, during heat injection, are the theoretical minimum temperatures. Basically, if you say, okay, we need to inject a certain amount of heat into the ground in each month, there is a minimum power required for it in order to make sure that if we have 100% this power during the month, 730 hours long, we will end up with this profile. So basically what this means is that our fluid temperatures during peak cooling will overlap with our baseload temperatures. So our profile would look something like this, where you see that indeed in summer our green line for the baseload temperatures overlap with our fluid temperatures during peak cooling. Because when we assume there is no peak power for cooling, well, we just end up with the baseload power that is required in order to deliver the energy to it. Now, question 1.2 was also about these temperature profiles, where we said, well, we made a simulation and we had an undisturbed ground temperature of 11 degrees Celsius. And we did our simulation and we ended up with 0.2 degrees Celsius as a minimum temperature in the end. Now, imagine we do a TRT and we find out that our undisturbed ground temperature is actually 0.5 degrees higher. How would that change our temperature profile? So basically, if you try to answer this question, you need to distinguish between your fluid temperatures and your borehole wall temperature. So what happens in this case is that we have a borehole wall temperature, which then is used with the effective borehole thermal resistance to calculate the fluid temperature. But since now our borehole wall temperature is 0.5 degrees Celsius higher, also our fluid temperatures will be 0.5 degrees Celsius higher. So we won't have 0.2 degrees Celsius in the end, but 0.7 degrees Celsius in the end, since it's all related with the initial ground temperature. And when that changes, all the other line changes as well. Now, I just want to say this is conceptually the correct answer. In part 3, we will see that also the borehole resistance, etc., is temperature dependent. But conceptually, when your initial ground temperature is higher, all your lines will move up to the same degree. Question 2.1 was then more on this effective borehole thermal resistance, saying, well, we have now a single U-tube instead of a double one. How would that change the effective borehole thermal resistance and also our design? Now, there is no definitive answer to this, as there almost never is in this domain of engineering. So what we need to distinguish about is the fluid regime. Because if we have a W probe, which is in a laminar flow rate, and we have not so good convective heat transfer from the fluid to the pipe, because it's laminar, but we have quite a good contact area. We have 2 U probes, so we have a lot of surface area to exchange heat. If we move to a single U-tube and the fluid becomes turbulent, because now, well, twice the amount of fluid is passing through a U-tube, so it could be that now our fluid is turbulent, meaning that our convective heat transfer is way better, that it compensates for the fact that we now have only half the amount of surface area to transfer heat. So if you go from a laminar to a turbulent flow when switching from a double to a single U-probe, it could be that the single U-probe has a better borehole thermal resistance and hence also a slightly lower total borehole length. So it's actually also cheaper looking at the installation or the drilling costs. Now the situation changes a little bit when we already have a W probe, or perhaps you're working with water and your W probe is already turbulent. Or you have a very deep borehole with quite a high flow rate and you have a turbulent W probe. If you then go to a single U, yeah, you were already turbulent, so you already had that very good convective heat transfer, and now you basically only lose half of your contact area. So then it's worse. And if you go from a laminar to a laminar flow, so your flow rate is extremely low in a W tube, and you go to a laminar flow in a single U tube, there is also no benefits. So in these last two cases, a W is probably the best looking at the effective borehole thermal resistance and also your borehole length. Now, there's way more nuance in this question, and we will come back to that later in this course, because you can also say, okay, let's vary pipe diameter, etc., etc. But just at the moment, this is a little bit how you should think about this problem. Try to compare and take both things into account, both the contact area of your pipes as well as your fluid regime. Now, in question 2.2, we were thinking about not crowding our boreholes, so legal aspects aside and also cost aspects aside. Is this a good idea to fill your borehole with groundwater? Now, it depends a little bit on your profile, your temperature profile, or your load profile from the building. Because we know that when we have this buoyancy effect in our borehole, we have 2 to 3 times the conductivity of static water. And static water has a conductivity of 0.6 watts per meter Kelvin, and then we end up with 1.2 or 1.8 due to this buoyancy effect, which is quite good and actually as good as if you would have crowded the borehole. Now the situation changes a little bit when you go to negative temperatures, because then the fluid starts freezing and this buoyancy effect, it goes away. And you will end up with the conductivity of static water, which is actually worse than what you would have had if your borehole was actually grounded. So here there is a trade-off between, would I drill more in this case in order to make sure that the temperatures are good, or we have enough borehole length to work with this worse effective borehole thermal resistance? Or should I grout my borehole to make sure that if we go to really cold temperatures that we have still this good thermal conductivity in the borehole? So that's a design question. The only thing I personally know is that groundwater filled boreholes typically occur when the boreholes are rather deep in the Scandinavian countries, when it's also very cold. So just looking at that, yes, it might be a good idea to consider it, but please take into account that your buoyancy effects will go away when you are freezing your system. 3.1 was about the long-term effects of the borehole. So if you say we have a perfectly balanced bore field, so we do not have a long-term temperature drift, and we have a groundwater flow, well, will this have a positive or negative impact? We know that groundwater flows take away part of the energy of your bore field. So if you have an imbalance and your ground cools down year after year, having a groundwater flow is actually really great, because part of your imbalance will be taken away with the groundwater, so to speak. So your temperatures stay more level. But in this case, you might be tempted to say, well, we already are balanced, so it does not matter. But that's not really the case. Because if you recall, our bore field is really a way to store energy over the seasons. It's a seasonal thermal energy storage system. So what this means is that in winter, we extract heat from the ground, so we store the cold, And we want to keep that cold in order to be able to cool passively or cool actively our buildings. But if we have a groundwater flow, part of this stored cold, and vice versa, the stored heat from summer, will be taken away. So this means that if you have your temperature profile, that since we have this groundwater flow and the energy is not stored as much, that our temperatures are actually closer. Our sinusoidal amplitude is actually a little bit smaller. And this could have a negative effect on your design. For example, and we'll come back to that to a later question, if we have a really high cooling need of our building, yeah, we really want our stored cold from winter. We need that in order to make sure that we can deliver the cooling to the building. But if our groundwater takes that away, yeah, perhaps we need an extra borehole to compensate for that and still make sure that we can deliver the cooling to the building. So yes, it can also have a negative effect when our bore field is perfectly balanced, both on the design aspects, but also on the efficiency of your total system, because part of the energy that's stored goes away. So your total seasonal storage efficiency goes down. So that's a little bit the nuance there. Now, in the last chapter of the second part, we made our first simulation in GHG Tool, and I encouraged you to play around a little bit more. So if you recall, we ended up with a system which had a single DN40 probe filled with water. It was already turbulent, and we played already around with quite a lot of parameters. And I asked you, well, how could we even improve on this design? And there are a couple of things, but the one that's the most trivial, let's say, is we did not enhance our grout. Throughout the whole exercise, we worked with a grout with the conductivity of 1.5 watt per meter Kelvin. But if we would go to a thermally enhanced grout of 2 watts per meter Kelvin, yeah, our borehole effective thermal resistance would again be lower, and also our temperatures would be lower. Now, that's the only thing we could do. We could also, for example, which is a little bit more far-stretched to be honest, decrease the borehole diameter, because that's also a way to decrease the thermal resistance from the pipe to the borehole wall, because we have less drought to pass through. So that's also something we could change. And another thing we could change is, instead of saying, okay, we have a DN40, but perhaps we could go to a single DN45. As long as we stay turbulent, our convective heat transfer will be really good, and going to a larger pipe diameter, as we also saw going from a DN32 to a DN40, having more surface area to exchange heat is also beneficial. So that's also an interesting way to go down or to explore. And it's just to show that you have so many flexibility, so many instruments you as a designer can use to fine-tune the design of your bore field. It's really fun when you get used to it. So these are just a couple of ideas on how you could even improve on this design. Now, question 4.2 was about the assumption of the ground temperature. It was located in the city center of Ghent. And for those of you not living in Belgium, that's a city that has a medieval history, so it's really old. So chances are that there is quite some urban heat island effect going on, and that our ground temperatures are actually higher than what our linear model, and which we discussed in part 1, predicts. So how would you take that into account already in a feasibility phase? So what you could do in that case is saying, okay, and we calculate our undisturbed ground temperature, and we could now say, okay, let's assume it's 0.5 degrees higher. That's sort of worst case, because in our design we were caring quite a lot about cooling, and we were always at the maximum temperature limit. So if we say it's 0.5 degrees higher, and we enter it manually, we could in fact also simulate that. And then you will see that in our case, you would need a couple of tens more boreholes in order to compensate for that and make sure that our cooling can be done in a passive way. So that's a way how it can be done. And perhaps especially in the case here, the size of this project, I would highly recommend doing a TRT test just to know the initial ground temperature, because it will determine, quite significantly how many boreholes you would need. And the last question was about a parameter we did not yet discuss, but in our general tab, we said, well, our simulation period will start in January. And then we start with winter and then summer and so forth. Now, you might argue, well, what would change if we start in June? And does that change our results? Now, as I mentioned already in this video, we are working with seasonal thermal energy storage. So if you start with January, you start actually with extracting heat from the ground and loading the ground with cold for summer. Right? That's what you're doing. So this means that when going into summer, your ground or your borehole wall temperature is actually already lower than your undisturbed one. So you stored already some cold, which is beneficial if you're having quite a high cooling load, because then since you have colder ground temperature, you can get away with more cooling. But if you would start in June, you don't have this. So your borehole wall temperature will be higher when you start in summer, meaning that also your fluid temperatures will be higher. And I just simulated that for you here. So we took the last scenario of chapter 4, and we simulated this with just starting in June. And what you can see is that we now cross our 17 degrees limits, which we did not do before. It's only 0.4 degrees Celsius on the top of my head. But that's due to the fact that we did not have this storage cold from winter. So I hope you found these questions interesting. Perhaps you learned a thing or two. Please also check out our textbook. More explanation is given there. I just want to go over the different questions also, face to screen basically. And I'm looking forward to seeing you in part 3 of this course, where we will dive more into the more advanced methods to simulate these temperature profiles and what other extra insights we can get from that. So I'm looking forward to seeing you in part 3 of this course.